Every time an AI system finds a relevant document, recommends a product you might like, or understands that happy and joyful mean roughly the same thing, it's using embeddings. Embeddings are quietly behind almost everything useful that AI does with language, and yet most explanations of AI skip past them entirely. Here's why that's a mistake. Once you understand embeddings, you understand how AI actually represents meaning, not as words but as points in a geometric space where similar things end up close together. That one idea unlocks how semantic search works, how recommendation systems work, and why retrieval-augmented generation is possible at all. Let's start with the problem embeddings solve. Computers work with numbers. They always have. A CPU doesn't understand words. It understands bits, integers, floating point values, so when you want a computer to work with language, you need a way to convert words into numbers. The naive approach is simple. Give each word a unique ID. Cat is word 4,721. Dog is word 9,043. Feline is word 3,208. This works for storage and retrieval, but it loses all meaning. Word 4,721 and word 3,208 have no relationship in this scheme. The number 4,721 is no closer to 3,208 than it is to 9,043. The structure of the number space tells you nothing about the structure of the word space. Embeddings solve this by mapping each word, and later each sentence, paragraph, or document, to a point in a high-dimensional vector space. Not a single number, but a list of hundreds or thousands of numbers. The critical property is that these vectors are arranged so that semantic similarity in language corresponds to geometric proximity in the space. Cat and feline end up close together. Cat and dog end up somewhat close. They're both animals, both pets. Cat and automobile end up far apart. The geometry of the space encodes meaning. This sounds abstract, so let's make it concrete. Imagine a simple two-dimensional space. You could place words on a map. Animals cluster together, vehicles cluster somewhere else, emotions cluster elsewhere again. Similar words are neighbors. The further apart 2 points are, the less related the concepts. Real embeddings work in hundreds or thousands of dimensions rather than two, which means they can capture far more nuanced relationships than any 2D map could. But the core idea is the same. Meaning becomes geometry. One of the most famous early demonstrations of this was that you could do arithmetic on embeddings and get sensible results. King minus man plus woman produced a vector that landed close to queen. The model hadn't been told anything about royalty or gender. It had inferred those relationships from the structure of language in its training data. How does the model learn to place words in useful positions? Through training. The original insight from a technique called word-to-vec was that you could train a model to predict a word from its context, or predict the context from a word. Words that appear in similar contexts end up being assigned similar vectors. That's how happy and joyful end up close, but they appear in similar sentences, around similar words, in training data. Modern embedding models are more powerful than early word vectors. They're context sensitive. The same word gets a different embedding depending on what surrounds it. Bank near river ends up in a different location than bank near account. This is the transformer architecture doing what it does best, building a representation of each token that's informed by everything around it. There's another important leap beyond individual words: sentence and document embeddings. Early approaches embedded words in isolation. Modern models can take an entire paragraph, or a full document, and produce a single vector that represents its overall meaning. This is what makes document-level semantic search possible. You're not matching individual words against individual words. You're comparing the meaning of an entire query against the meaning of an entire passage, compressed into a single point in the vector space. Training these models takes a different approach than training a language model from scratch. One of the most effective techniques is contrastive learning. The model is shown pairs of semantically similar text, a question and its answer, a sentence and a paraphrase of itself, and trained to pull their embeddings close together in the vector space. It's also shown pairs of unrelated text and trained to push those apart. After enough of this, the geometry of the space reliably reflects semantic relationships. A practical challenge that comes with embeddings at scale is storage and search. A real-world system might need to search across millions or billions of embedded documents. Comparing a query vector against a billion stored vectors one at a time is too slow. This is why vector databases exist, specialized systems that organize embeddings spatially so that nearest neighbor search can be done in milliseconds rather than hours. Tools like FIS, Pinecone, and Weaviate are built specifically around this problem. The most direct application is semantic search. Traditional search matches keywords, search for car repair, and you get results containing those exact words. Semantic search uses embeddings to find results that are conceptually related, even if they use different words. A query for car repair might surface a document about vehicle maintenance or fixing an automobile, because those documents produce similar embedding vectors. The search is over meaning, not text. Recommendation systems use the same idea. Represent a user's history as a set of embeddings, average them into a single point representing their interests, then find the nearest items in the embedding space. Nearest in the vector sense means most conceptually similar to what this person has engaged with. Netflix, Spotify, Amazon, all of these rely on some form of this architecture under the hood. Retrieval Augmented Generation, RAG, which came up in the hallucination video, is directly built on embeddings. When you give an AI assistant access to a document collection, the system pre-computes embeddings for every chunk of every document. When a question arrives, the question is also converted to an embedding, and the system retrieves the document chunks whose embeddings are closest to the question. Those chunks get passed to the language model as context. The language model never had to memorize the documents. It just reads the retrieved ones at inference time. This is why RAG reduces hallucination. The model isn't recalling from weights, it's reading text that's been verified to be relevant. The embedding retrieval does the selection work. The language model does the reading and reasoning. There's another application worth understanding: classification and anomaly detection. If you embed a large collection of support tickets, spam emails, or financial transactions, unusual points in the embedding space, things that don't cluster with anything else, stand out as anomalies. Things that cluster with known fraud transactions can be flagged as likely fraud. The geometry of the space makes structure visible. What's remarkable about modern embedding models is how transferable they are. A model trained to embed text for one purpose, say semantic search over product descriptions, produces vectors that work well for entirely different tasks: sentiment classification, duplicate detection, clustering. The underlying geometry of meaning is stable enough that a single model's embeddings are broadly useful. Here's the mental model worth keeping. Language is not numbers, but you can convert language into a geometric space, a high-dimensional map where meaning becomes distance. Words, sentences, documents all become points. Similar things end up close. Different things end up far apart. This representation is what allows AI to search by meaning instead of keywords, to find related content, to retrieve relevant documents for a language model to reason over. Embeddings aren't the most visible part of AI, but they're load-bearing. Take them out, and the whole structure of modern AI, from search to recommendations to RAG to classification, comes down with them. If this kind of systems-level thinking about AI is what you want more of, subscribing is how you get the next one.